The Bernoullis. If you've hung around any mathematician long enough, or done a little extra research yourself into any of maths, engineering or physics, you may have heard the name Bernoulli. It belongs to not just one, but 8 very prominent Swiss mathematicians from a few generations of the same family. The sheer volume of talent in this family dominated the academic world in the fields of physics and mathematics for the best part of the 17th and 18th centuries. Now, as you will have guessed from the title of this video, familial unity was not a key component of their collective successes. Here, we're going to focus on 2 of the elder mathematicians in the family, Jacob and Johann Bernoulli, both sons of Margareta and Nicholas Bernoulli, who was a magistrate and owner of a successful spice business in Basel, Switzerland. Jacob was the eldest, and 12 years Johann senior. Jacob, or Jacques, or even James if you fancy, because he was actually known by all 3 names, was born on the 6th of January 1655 in Basel. Due to pressure from his father, he was forced to study theology and philosophy, eventually graduating from the University of Basel with a master's degree in philosophy in 1671, as well as a licentiate in theology in 1676. However, fortunately for the mathematics world, he decided that this was not nearly enough for a young man to get his head around, and had chosen to study astronomy and mathematics as well, in spite of the wishes of his parents. After finishing his theology degree in 1676, he began venturing across the continent, coming across some fascinating areas in both the mathematical and scientific world. From 1676 to 1682, he found himself travelling through Europe, initially visiting France to study the works of Descartes, before heading to the Netherlands in 1681. By now, his passion for mathematics and science was burning, so England was his next destination, resulting in his meeting with Robert Hooke, most well known for his contributions to physics, in particular Hooke's law. In 1683, he returned to Switzerland to teach mechanics at the University of Basel, on the way turning down the chance to use his theology degree and work in the church. His real passion lied in mathematics and physics, and in the following years he would go on to contribute tremendously to the mathematical world. Johann was born on the 6th of August 1667, and after working in the family business for a year and disliking the work intensely, he followed his brother Jacob to the University of Basel in 1683, where he studied medicine and was tutored by Jacob in mathematics on the side. He turned out to be a prolific student and was his brother's equal in mathematical skill within 2 years. Now, Jacob would go on to be mostly known for his contributions to probability theory, yet his magnum opus is perhaps his discovery of one of the most important constants in mathematics, E. Nowadays, you might hear it referred to as Euler's number, but it was Jacob who first found its value. Whilst tackling a question in 1683 regarding compound interest, which involved finding the value of the limit of 1 plus 1 over n to the power of n as n tends to infinity, Jacob found that the value tended to 2.71821 and so on. Thus the constant E was discovered. The applications of this constant in mathematics are endless, and it features alongside 4 other constants I, pi, 1 and 0 in Euler's identity, which says that e to the power of I times pi plus 1 equals 0. This identity is often referred to as the most beautiful equation in mathematics due to its demonstration of the connection between maths' most fundamental constants. There are some standout applications of this constant. For example, e to the power of x is the only non-trivial function for which it is its own derivative and antiderivative. In other words, if you integrate or differentiate e to the power of x, you will get e to the power of x. Because of this, the family of functions y of x equals a times e to the power of x, where a is any real number, is the solution to the differential equation y dashed x equals yx. In probability, e also appears frequently. Here's an example. Suppose a gambler plays a game with probability of success being 1 in n, and they play the game n times. What you find is that as n grows larger, the probability of every outcome being a failure tends to 1 over e. Another real-world use is that the constant is actually used in finding the half-life of radioactive material, which is the time it takes to decay to half of its initial value. Despite being brothers, and Jacob having taught Johann when he was younger, they hardly ever worked together on research. Instead, they often worked separately on the same problems. One of the first of these was a problem proposed by Jacob, which consisted of finding the shape of a ship's sails when filled with wind. The representative curve is called a catenary. A catenary is the curve that an idealized hanging chain or cable assumes under its own weight when supported only at its ends in a uniform gravitational field. It had first been discussed by Galileo Galilei in 1638, who recognised its difference from a parabola, and its mathematical properties were studied by Robert Hooke in 1670s. Mathematically, it is portrayed as the graph of the hyperbolic cosine function. Hyperbolic functions are similar to the regular trigonometric functions sine, cos and tan, but they're defined on a hyperbola rather than a circle with radius 1. Johann succeeded in finding the curve and provided a full solution, which was his first important mathematical result independent of his brother. He then proceeded to boast of his achievements, rather loudly. This caused Jacob to retaliate in print, claiming that Johann's only achievement was repeating what his tutor, Jacob, had taught him. The public squabbling escalated in tension from this point onwards as the two developed a jealous and competitive relationship. Meanwhile, the two continued to work on their own studies. One of Jacob's most notable works came in 1689, as he published Bernoulli's Theorem, or what is now known as the law of large numbers, a key theorem in probability theory. This law states that the more times you perform a trial, the closer the average of the results will be to the expected value. For example, if you toss a coin 20 times, you might expect to get 10 heads and 10 tails, but you've possibly seen from your own experiences that it is not uncommon to get, say, 14 of one and 6 of the other. However, if you are bored or boring enough to toss the coin 20,000 times, it will be much more likely that you get very close to 10,000 heads and 10,000 tails. The likelihood of the numbers being split equally increases with the more tosses that you do. Now, that is cool, but what use is this to people in real life, I can hear you ask? Not to worry. There are plenty of examples where this law comes in handy. In finance, for example, the Monte Carlo simulation model is used to determine the probability of different outcomes when there are random variables present by assigning different values to these variables and averaging the results. Now this is relevant to the law of large numbers because doing these simulations a large number of times gives a good approximation of the outcome. This is vital for considering the risk and uncertainty involved when making investment decisions. Have you ever seen someone playing roulette get on a winning streak and then just suddenly walk away and quit whilst they're ahead? Now, the chances are that you've seen a gambler that knows the law of large numbers. They know that, although they're currently winning more regularly than expected, this will even out as they play more. So, they recognise that they've had good fortune and stop before they gamble their winnings away again. Not wanting to be in his brother's shadow, Johann was eager to have success on his own. In 1694, he was successful in integrating differential equations, and this won him offers of 2 chairs in mathematics at the universities of Halle and Groningen. He wanted to stay at Basel, but the mathematics chair was already commandeered by his brother, another reason for growing resentment towards him. Johann, his wife Dorothea Faulkner, and their 7-month-old newborn, who, shock horror, would grow up to be a budding mathematician, departed for Holland in 1695 to the University of Groningen. During his time there, he tutored Marquis de l'Hôpital and signed an agreement to send all his discoveries to the tutee in return for a regular salary. Unfortunately, this resulted in one of Johann's biggest contributions to calculus being known as L'Hôpital's rule, as Marquis published the result as his own. In 1696, he proposed the brachistochrone problem as a challenge to other mathematicians. Initially, he gave them 6 months to solve it, but this was extended to a year and a half. The problem was as follows. Find the shape of the curve down which a particle slides from one point to another under the influence of gravity in the least time, without friction. 5 correct solutions were received. 4 of these were named, and 1 was anonymous. The named ones were from L'Hôpital, Leibniz, Jacob, and Johann himself, and the anonymous one turned out to be from Sir Isaac Newton. This resulted in Johann then commenting ex unge leonum, excuse my poor Latin, translating to tell a lion by its claw, because Newton's solution was incredibly distinctive in style. The problem is solved by using an integral in the equations for speed, which uses the conservation of energy. An integral in mathematics is either a numerical value equal to the area under the graph of a function for some interval, or a new function, the derivative of which is the original function. And hence, the answer to this problem is a fragment of an inverted cycloid. A cycloid is the curve traced by a fixed point on the perimeter of a wheel rolling along a straight line. Actually, Johann had originally found an incorrect proof to show that the optimal curve is a cycloid, and the competition actually provided him an opportunity to substitute his brother Jacob's correct proof as his own when he published his solution. This prompted a complete breakdown in their relationship. Jacob's contributions to mathematics and physics continued up to his death in 1705 and beyond, with his highly regarded piece of work Ars Conjectandi being published in 1713 8 years after he had died. This work would go on to be considered a landmark in the field of combinatorics and was the foundational work for probability theory. For Johann, he and his family set off to return to Basel in 1705, initially with the intention of being the Greek chair at the university. They discovered Jacob's death whilst travelling, and this left the mathematics chair open for him to obtain. He went on to fill his brother's empty post. When all was said and done, Johann arguably exceeded his brother in the number of contributions he made to the field of mathematics, with discoveries in integral and differential calculus, found in the calculus of variations, and working almost purely with mechanics in his later years while tutoring Leonhard Euler. He died at the ripe old age of 80 in 1748. The feud between the brothers is a common thread through mathematical discovery and academia in general. But do these squabbles between researchers help or hinder their academic progress? There's an argument to be made for both sides here. The element of competition between people can provide motivation to outperform the other with more dedication and effort poured into the topic. This is shown by the Bernoullis and countless others with the drive to beat and overshadow their rivals. Would they have been pushed to the discoveries they made without the pressure of this competition? In contrast, it could have been beneficial to the field if some of these great academics had worked together. The adage that two heads are better than one does hold true after all, and very rarely is any new research completed totally singularly, without use of any previous work or help from others. In the Bernoulli brothers' case, we do not have the luxury of what if, but it seems that the competition element here pushed the two of them to further research. Even if collaboration was the key to their full potential, no one can deny the extreme lengths to which mathematics was dragged forward by their collective discoveries.